Okay, good.
Right, good afternoon. As Dr. Moore already said, I decided to do a project on data science, and through his guidance, I came up with this project for my undergraduate degree. So my name is Samuel Dassi from the Department of Mathematics. So let me start with my presentation on neural network parameter estimation. So I considered those with vaccination and, more importantly, timely and delayed diagnosis of the virus. So,
Okay. Okay.
so in my presentation, I'll talk briefly on integration, where I will discuss some history of the virus in the world and in Ghana. Then I'll give out the model formulation that I used for my project. Then I'll go deeper into neural networks and explain how it works. Then I have some results and simulations that I got from my Python programming. Then I'll conclude. To begin with, as integration, if you look at the global perspective for COVID-19, machine learning is usually what the world is going towards in predicting its behavior. So I intend to use machine learning and neural networks to study the behavior of COVID-19, especially in Ghana. So I used a 200-day period to generate data points, about 1,000 data points through Python. Then I implemented the deep neural network approach to study the behavior of the pandemic in Ghana. I used the mean squared error to evaluate my model, which the value was actually quite okay. For historical perspective, as the first speaker said, the disease was first discovered in Wuhan, China in 2019, but in the following year, 2020, WHO declared the virus as a pandemic. Considering the perspective of Ghana, ours was recorded on 12th of March 2020, where two diplomats from Ghana were coming from Norway and Turkey, and they got the virus and were immediately quarantined. So the government from then decided to put up some protocols through testing, contact tracing, and then public education. This, despite all this, we had some infections. As at June 2023, we had about 171,000 confirmed cases in Ghana with 1,462 casualties. So going to my model, this is a model I designed myself using Microsoft Word with 9 compartments. We have the vaccination or vaccinated class, which I use V to represent. Then we have the susceptible population for S. Out of that, those who were self-quarantining, I represent with SQ. Then we have the exposed population. Then those who were exposed, some were infected. From the infection, we classified them into two: those who had delayed diagnosis and instant diagnosis. So I1 for the instant, and then I2 for the delayed diagnosis. Then those who were infected were actually hospitalized, and that led to viral spread in the community, which I represent with VS. Those who were hospitalized fortunately got recovered and removed from the population. And at the time that there was no vaccination, those people were actually reinfected. So they became susceptible to the disease again, coming back to the S. So the flow diagram gave us an ODE, a system of ODEs presented by this. Yes, so this is the system of ODEs I have for my model. So as I said during the the flow diagram, these are the meanings of the compartments. We have the vaccinated class, which is V, susceptible, which I use S to represent. In the self-quarantined susceptible population, I use SQ. The E for the exposed population, I1 for the infectious with timely diagnosis, then I2 for the delayed diagnosis. Then H for the hospitalized, those with the, we have virus spread in the community through physical touches and co. So I use VS for that. Then the R for recovered population. Then N, then we have the total population of the country, which I use N for. Okay, so the parameters in the model, as we can see in the model, the various parameters, the values for them from literature are these, which I got from literature. So we know that most models or every model relies on data. So I used, as I said in the beginning, I used 1,000 data points for my model, which span from 0 to 200-day period or periods. So initially, everybody started as a susceptible population. And so far as you are in the society, you are likely to be infected. So you are susceptible to the virus. Now, going deeper into neural networks and how it functions, some may ask, what then is a neural network? So the first speaker explained most of the concepts of neural network, but basically, it's a type of machine learning algorithm that is modeled after the way the human brain functions. So anytime we receive an impulse, the brain processes that and then gives an output, which we react to. Then we usually every model or neural network has nodes. As where in the human system, you have the neural system. It has nodes that functions in similar way. So the first layer of the network is actually an input layer, which receives the data, then processes it and gives out an output, which basically will be a feedback or a prediction or a classification. So one good thing about neural network is that it's able to recognize complex patterns in data and be able to make predictions. So this is a typical example of a picture of how the neural network behaves. So we have input layers, which are the data you feed into the system. Then we have hidden layers, as many as you will have. So we have three, in this case, we have three hidden layers, which are interconnected using nodes or neurons. Then after processing, it gives an output, which the output layer produces. So I was saying earlier that the neural network behaves in a similar way as the brain behaves. So the brain receives inputs from society, maybe through a touch or a smell or what we hear, then processes it and gives a feedback. So the same way the neural network behaves, gets data from the society or from the sources that then it processes it and gives predictions or classification. So I spoke on this, how it behaves. So basically, during training of the neural network, there's something we call weights and biases. These nodes adjust the network so that it can accurately predict what you want to predict. In this case, COVID-19 infections. So how is this prediction done? Basically, it compares the predicted value after the processes. It compares the predicted value with the actual data output that you have. Then there's a difference. That difference is what we aim to minimize for a good model. So usually we have the iterative process of processing the data. So it goes through the system, compares the error. If it's too big, then it comes back through a process called backpropagation, then goes to the system again until we have a minimal error. Then if that minimal error is okay, then it gives an output. Okay, so I was explaining the picture of the neural network, and I mentioned these concepts. An input, which is really the data you feed into the system. The weights are the parameters that we aim to predict. Then we have the activation function. Usually, most data, we don't have a linear data or simplified data, so it's always complex. So we have activation function that introduces nonlinearity into the system, able to study the complex nature of data. Then we have an output, which basically represents the predicted values from the process. So in my model, I used two activation functions, the rectified linear unit or ReLU, and then the hyperbolic tangent function or tan function. The ReLU actually, what it does is that anytime there's a negative value in the data point, converts it to zero and keeps the positive values intact. So for the hyperbolic tangent function, it tries to normalize the data between -1 and 1. So anything outside that is compressed within the interval of -1 and 1. Okay, so I mentioned that the neural network behaves or uses some concepts, and I mentioned backpropagation. But before the backpropagation, the normal thing we have is the forward propagation, which is the processing of the data from an input through the hidden layers to an output. So that is basically the forward propagation. Then after the forward propagation, the output is compared with the actual data output. Then if the value or the error is too huge, it undergoes what we call the backward propagation or backpropagation. Back into the system, then processes it again, then gives us a lower or smaller error value. So basically that is what happens there. Now, there's what we call learning rates. In neural networks, we have to use hyperparameters to do the training, and one of them is learning rate. So what happens is that the way the iteration is done depends on the learning rate. So it gives us a way of controlling the step size of the process. So during training, the learning rate tells or determines how quickly or slowly the model is able to learn from the data. So a good learning rate is very important in neural networks. Generally, they use a learning rate of between 0.000001 and 0.1, but I choose 0.001, which falls within the interval given. So how then do we schedule a learning rate? So I use the cyclic LR scheduler to implement the cyclical nature of the learning rate. So what happens is that it varies the learning rate between the minimal, the smaller, which is the 0.000001, and then the maximum of 0.1. So we don't have a fixed value for the learning rate. It varies between that interval so that we have a good prediction. So I use the stepping size of 4,000, which indicates the number of steps to increase the learning rate from the base, the minimum to the maximum learning rate. So the first speaker spoke on an optimizer. For me, I use Adam optimizer to optimize the parameters. So during the training process, the learning rates may not be fixed or should not be fixed. So what the optimizer does is that it varies and it makes adaptive to the various parameters. So yeah, that is it. So when the optimizer does its work, then we have an error. How then do we calculate or get an error? We use the loss function to do that, which measures the differences between the predicted output and the actual output in the data. basically, for me, I use the mean squared error to do the evaluation. So the primary goal of the training process is to minimize this error value or the loss value. So to minimize that, there's what we use, what I call the gradient descent to do the optimization, which it helps us to minimize the loss function well. Okay. So from all this neural network stuff, I have some results that I have some results. So as a recap, this is a model, the system of ODEs that I used. So these are the parameter values. And then the graph for the ODEs are this. We see that I picked out only the disease-induced compartment from the model to see how the various parameters affect those disease-induced compartments. So we had the vaccinated, which is the green line, which peaked probably in the first 10 days, it peaked and it started to fall. You have the exposed, which is relatively high because most of the population are exposed to virus. Then the infectious with timely diagnosis, infectious with delayed diagnosis, and then the hospitalized population fall within. We are still relatively high despite the measures put in place by the government. So how then did I work on the parameter estimation? So I use a Python library called PyTorch to do the training. So during the training, we're able to find values that's able to minimize the error in the model. So the smaller the value of the error, the better the performance of the model. So during the training process, the estimated parameters were compared to the initial parameter values that we got from the literature. So after comparing, then we got these values for the parameters. So we can see the future values and then the neural network predicted values or values that we have. I said that earlier that the parameter values were actually squashed between -1 and 1. But in this case, we have all positive values because of the value activation function. Okay, so the result from the neural network parameter sets I used them to make predictions for 300 days. Initially, I used 200 days for the data. Now I have 300 days so that just to expand the reach of the model. So we can see that from the model, initially we saw this behavior. So using the neural network values for the parameters, we saw that the exposed population is relatively high, but quickly plateaued and started to fall. Then the last compartment to plateau was I think the hospitalized, basically because initially the number of births in the country and then infection and the vaccination wasn't that much in Ghana. So we see that it took longer time for that population to plateau and start to fall. Yes. So now to work on sensitivity, I used three of the compartments, three of the parameters to study the behavior on each of the compartments, usually the disease-induced compartments. I used the self-quarantine rate, the vaccination rates, and then the recruitment rate to study the behavior of the compartments. So the first parameter I used is the self-quarantine rate. So we see that as the rate of self-quarantine is increasing, the number of people hospitalized decrease. So if you quarantine, it helps to reduce the number of people who are exposed to the virus and probably going to be infected and hospitalized. So it's good that with the education then to reduce the infection was to be at home, nothing to be outside. That's self-quarantine. Then for the similar behavior, the more people that self-quarantine reduces the rate of exposure to the virus. Now, considering the timely and delayed diagnosis, it's quite interesting to note that for those who self-quarantine, the you see the behavior of the curve, it plateaued quickly because we are able to quickly determine or detect the disease and then treat them. So we have the timely diagnosis there. But for the delayed diagnosis, it took longer time for the diagnosis to be done. So we see that people with the virus in the society taking longer time to plateau and start to decrease. Now, one problem I encountered was for the recruitment rate on the compartments. We see that there's no visible effect of the treatment rate on the disease-induced compartments. You can see that in the hospitalized class, the exposed class, and the timely and delayed diagnosis instances. So this is a challenge I encountered, which may be resolved later. Yes, so that is it for the vaccination rate. So we see similar behavior. There's no much visible effect on the vaccination rate on the compartments. Now, after getting the parameters from the neural network, I wanted to see the behavior or how it's going to predict, comparing it with the data I have and then the neural network parameter data. I see that the dashed lines represent the predicted values for the compartments. But you see that they all fall within this on the same curve. That means the model is able to learn excellently well, though we see some misbehavior in the simulations. So we see that there's no difference between the actual data and then the predicted data from the model. Okay, so I mentioned that how I evaluated my model. So I used a loss curve to trace the behavior of the errors. So as the epoch increase, we see the error decreasing. So at the point of 20,000 epochs, we see the minimal error value. So I could have stopped at 20,000 epochs, but decided to explore what happens after the 20,000. So we see a stable behavior there. I increased it to about 150,000 and started going up again. So I started to stop at 100,000. So in conclusion, I focused on the focus of this project was to use neural networks to estimate parameters for COVID-19 in Ghana. And I considered the vaccinated and timely and delayed diagnosis instances. So basically, I aim to develop a model that could accurately estimate the parameters of the COVID-19 infection in Ghana and study its transmission dynamics. The result obtained highlight the importance of considering the vaccination instance and timely diagnosis of the virus to model COVID-19 instances. Since these two guys had significant effect or impact on the dynamics of the disease. So for benefit's sake, policy implementers or policy designers can use this to help in developing effective model and study the behavior of diseases in Ghana and how to prevent same. So I mentioned as a challenge that the analysis and then the sensitivity wasn't that accurate in most of the parameters. So it's a challenge I faced. Nonetheless, the project demonstrates that neural network has the potential to be used to understand and model the transmission of COVID-19 in Ghana. One key challenge I faced, usually with